In this video, I want to introduce the experiment we will be doing in our next class meeting. The purpose of this experiment is to investigate the direction taken by a light ray when it crosses a boundary between different media. So we're going to have air on the one side of the boundary, and we're going to have a different material inside this dish. So the boundary we are interested in is this red line here. And in terms of the dish, that red line is the flat plastic edge of the dish. We would ultimately like to find a mathematical relationship between the angle of the incoming light ray, which would be called the incident angle, and the angle of the outcoming light ray. The outgoing light ray is in the oil, so the outgoing angle will be the angle of the light ray that is in the oil. The materials we will be using to explore this are the light box, which you saw last week. It will output a light ray, this semicircular dish, and a liquid that we will put in the dish. And you may have a different liquid, but for this example, I'll use oil. And I need to point out with the dish before I put a liquid in it that it has a straight scratch here on the flat side. That scratch is in the very middle of the flat side. The purpose of that scratch is to show you where to line the dish up, because it's important that all of these light rays are hitting this very point on the dish. So it's very important that the light rays all be hitting this point, which happens to be at the center of the circular curvature. Okay, so this is a half of a circle. This scratch marks the center point of that circular shape, and it's important that all of the light rays hit the boundary at that point, and you'll see, I'll explain later why that is. But that's why the scratch is there, and you need to make sure that you line the scratch up with this line here on your light path data sheet. So the boundary we're interested in is shown by the red line, air on one side. I am going to have oil on the other side of that boundary. Now we saw in class that when light travels in air, it takes a straight line path. And when it travels in the oil, it will also take a straight line path. The question we want to look at is what happens to that straight line path when it crosses from air into oil. Will it continue to go in that same direction, or will the direction change when it goes across that boundary? And we want to find a mathematical relationship between the incident angle, so the angle of the incident light ray, and the angle of the outgoing light ray. Remember that we always measure our angles from the normal, and the word normal means perpendicular, so you can see that this right here is perpendicular to the boundary that we are considering. So the incident angle for A, because light ray A is going to go in on the normal, the incident angle would be 0 for light ray A. For light ray B, you would need to use your protractor to measure this angle, and that would be the incident angle for B. For C, you would need to measure from the normal over to light ray C. So for this experiment, our independent variable is the incident angle, and the incident light rays that we will do are A, B, C, D, E, F, and G. They're already drawn for you. All the incident light rays will strike the dish at its center point, which is marked by the scratch. We will determine a value for each incident angle by measuring with our protractor from the normal to the light ray. And we will change the incident angle, so this is our independent variable, we will change it by moving the light box to cause a light ray to shine in at these different angles. Okay, so in the experiment you will need to place your light box on each of those different incident light rays. Our dependent variable will be the outgoing angle. So when you shine your light ray in, let's suppose that you find the light rays coming out over here. Then you will need to measure the angle from the normal over to that light ray to get the outgoing angle. And then I'm going to leave it to you to think about what we are keeping constant. What would it be important to not change while you are getting your data for this? Now let's do the first one together because it will help you understand why we are using this oddly shaped dish for this experiment. There's a very important reason why the dish is a semicircle shape, and I want you to understand that. So the first light ray is coming in along the normal. So here it is. I'm going to make it a little darker in here. And we can see that we have an outgoing light ray right here. So I'm going to trace the outgoing light ray. And you might be able to, if we poke around in here, you can see where the light is actually inside the oil. You can see that it's going in the same direction all along there, even inside the oil. So that means we can move the dish and we can trace back to show what the path was inside the oil. So for a light ray that has an incident angle of 0 degrees, we see that it had an outgoing angle also of 0 degrees. Now this is already telling us something interesting, which is that a light ray that comes in and strikes the boundary perpendicular to the boundary, right? So it's coming in on the normal, which means it's coming in at an angle that's perpendicular to the boundary. It continues without bending. It doesn't even change direction. And that is the reason that we use this specially shaped dish. And I'll explain that a little bit more in just a moment, but I want you to go ahead and think through what you expect for the rest of these. Do you expect light ray B to just continue in the same direction? Do you think light ray B will come out like this? Same exact angle that it came in at? Or do you think it will bend and go maybe closer to the normal? Or do you think it will bend the other way and go farther from the normal? So that's one thing we want to look at, is what happens to this outgoing angle. Is it always equal to the incoming angle, or is it smaller or bigger? Now I want to explain to you why we're using this very special dish. So the first important thing to know is the dish is in the shape of a half circle. The scratch on the side marks the center of the circle. Okay, so here's the circle, here's the center of the circle. If we draw a radius from the center to the edge, you will notice that that radius strikes the edge perpendicular. And that's true for any radius that you draw. It's going to be perpendicular to this outer surface. Now, why is that useful? Here's the reason that that is important. It means that no matter what direction your outgoing ray is, it's going to be traveling along a radius. Because all those outgoing rays are going to start here, and they're all going to start there because you're going to make every incident ray strike the dish here. So every incident ray strikes the dish here, which means that every outgoing ray has to start at that point. And no matter which way it goes from that point, it'll be going along a radius, which means that it is going to strike this other edge perpendicular to that other boundary. And because it's going to strike it perpendicular to that boundary, we know it's going to keep going straight past that boundary. And that means if you can trace a light ray out here, you can then move the dish. Okay, so if you trace a light ray out here with your ruler, you can then move the dish, and you can use your ruler to extend it back and figure out where it was inside, because you know that it did not change direction here because it hit the boundary perpendicular. So to review, the reason for the semicircular dish is that we are interested in what happens at this boundary, not at this one. And so to eliminate anything from happening at this boundary, we make sure that all the light rays that are going to hit this boundary are going to hit that boundary along a radius, which means that they're hitting that boundary perpendicular to the edge, and they will just continue in that same direction they were going.